Hello, and welcome to Astronomy 100. In a previous video, we began our discussion of telescopes, and we've had the luxury of being able to visit some of the places where some of the more famous telescopes and largest telescopes of the world are located. In this video, what we're going to do is continue our discussion of why astronomers use telescopes, and then we'll focus our attention on where do astronomers build telescopes. When they have a choice to place a telescope somewhere in the world, there are some very specific reasons and conditions that will make the decision and the determination for that. So let's get right into it. In the previous video, we saw that astronomers use telescopes for the primary purpose of gathering light. A telescope serves the purpose of allowing you to see very faint objects. Many of the objects of our universe are very far away, and so they look very faint. And so the ability to see these very faint objects requires a big telescope. The bigger the opening, or the bigger the bucket, if you will, to gather the light, the more light you can gather. And we gave the example of how a human eye has the ability to gather only so much light because the opening to the eye is essentially only so big. On a telescope, the opening to the telescope is often referred to as the objective of the telescope. And so each telescope in the world is always quoted not only as the name, typically the person who it's named after, but often it is named for the size of the telescope. The example that we had last time was that the largest telescope on Palomar Mountain at Palomar Observatory is called the Hale 200-inch telescope. The number 200 inches is referring to the size of the opening of the telescope. So it's very common that you'll hear telescopes quoted by name that has something to do with their size, because again, when it comes to gathering light, bigger is better. The human eye can only gather so much, but large telescopes can gather quite a bit of light. Now, the second reason why astronomers prefer to use telescopes is because with a telescope you get what's called increased resolution. So let's first define the word resolution. In this instance, in this usage, the word resolution refers to how we're able to see fine details in very small objects. So the ability to see these tiny details is called to resolve a small amount of information from an object. And so the resolution capability of a telescope is one that is very important because, of course, we want to see very fine details in very small, very distant, faraway objects. So increasing the resolution of what you're able to do or able to observe, increasing the resolution is a quality that the telescope has. Now, the way that this works, let me give you a few examples. This is a photograph taken of Coors Field. This is the place where the Colorado Rockies play baseball. And this is taken from a telescope that is part of a satellite that orbits the Earth. So this is how we look down on the Earth to take images of its surface. You've probably seen many, many different pictures of the surface of the Earth if you use Google Earth or something of the sort. Now, this photograph here was taken in a time when technology allowed only a certain quality of resolution, meaning the resolution capability was only so good. And even though you can clearly see that it's a baseball field here, and you could probably identify some of the larger features, notice that there are many things that can't really be resolved. You can't quite see the detail in the infield. When it comes to where the public sits, there's not a lot of information that can be revealed as well. The smallest thing that you can see in this picture is still quite large. But as technology gets better, the view of the surface of the Earth becomes better and the resolution becomes finer or smaller resolution, and you can see something like this. Notice that the higher resolution of the capabilities of the satellite now reveals lots of information. You can see the individual aisles, you can see information about the infield, you can almost make out some of the types of cars that are parked in the parking lot. So increasing resolution means the ability to see smaller and smaller details. Let's relate this to astronomy. Here's an image of a group of stars. And I know it's very tempting to think that this is just a blurry image, meaning a telescope that may have been out of focus. But in reality, this was a perfect focus for this telescope, the best focus that this telescope is capable of. What's happening is the resolution of the image is not very good. You aren't able to see fine details and very small things. But an increased resolution or a higher resolution image of the same group of stars would look something like this. And even though it's the same stars, notice now that you can see a lot more information that you would not have been able to see with a low resolution image. Let's go back one, and you can see that the resolution is actually quite a bit better. Another example would be this one here. This is the central region of a galaxy that is technically known as M51. Its nickname is the Whirlpool Galaxy. And at the time this telescope was taking the picture of this galaxy, this was the best resolution that you could get. In other words, the details that you see in this picture were just about as good as it can get. But higher resolution allows you to see finer details. And notice that an increase in the resolution allows you to see all sorts of details that have to do with the stars and the gas clouds and the dust clouds where these stars are forming. Let me again go back, and you can see that there's quite a bit of difference, quite a bit more information that you get with an increase in resolution. So how does a telescope help with this? Well, it turns out that the ability to see fine details, an increase in the resolution, has to do with the size of the telescope. And I'll get back to that in just a minute. So what we're going to do is define a particular term that's related to a formula you'll see in a second. Let's imagine that this is your eye, and this is the object that you're looking at. If you remember from a video, many videos ago, early in the semester, we talked about what was called angular resolution, or angular diameter was the term we used then. The ability to see the appearance of the size of an object. This person here is not seeing the true size of this object. This person is only seeing the appearance of the size of this object. Now this angle that represents the apparent size of the object, we're going to label it with the Greek letter alpha, where alpha represents the minimum angle that you can resolve, meaning the smallest thing that you're capable of seeing fine details in. Now it's important to remember that we want this angle alpha to be small. Smaller is better. So we don't want a large number as our answer. We want a small number because that's the small detail that you're going to see in some sort of an object. And here's the relationship. So the ability to see details, or the angular resolution of a telescope, is proportional to the wavelength of the light that you're looking at. In other words, is it visible wavelengths that you're looking at? Is it infrared wavelengths? Is it radio wavelengths? And then the D is the diameter of the opening of the telescope. In other words, the objective size, or the size of the bucket, the size of the barrel that the telescope has. What I want you to notice is that it's an inverse relationship between these two. Remember, we want alpha to be small. To make alpha small, we make D large. Remember the inverse relationship. The bigger D becomes, the smaller alpha becomes. So the ability to see smaller and smaller details will get better and better if you have a telescope that is larger and larger. So the larger the telescope, the ability to see finer details becomes more readily available. So to get small details very obvious, we need to build very large telescopes. When we combine this idea of increased resolution to the idea of the ability to gather light, what you can now see that both of these favor larger telescopes. Bigger telescopes, bigger buckets gather more light, and also bigger telescopes, bigger buckets make you see finer details by increasing resolution. Now, I'm going to show you an example here in just a second, but let me first give you an idea of one of the terms we're going to use in the example I'm going to show you. When astronomers measure angular size on the sky, we use a unit of increment typically called the degree. If you're familiar with geometry, remember that a circle has 360 degrees all the way around, and every degree is 1/60th of a circle. So the entire sky, all the way around, can be thought of as being 360 degrees. Let's imagine that these two lines, the separation between these two lines is 1 single degree, and to give you a sense of scale, the full moon is not even 1 full degree in size. It's about a half a degree. The problem is that 1 degree is a very, very large portion of the sky. And you can see easily that 1 degree would be still too big to measure the size of something like the full moon. So what we do is we take each degree and we divide it into 60 increments. And these increments are called arc minutes. And so 1 arc minute is 1/60th of 1 degree. Believe it or not though, 1 arc minute is still very, very big. And so what we do is we take each of these arc minutes, think of these 2 lines here as 1 arc minute, and we divide it into 60 more increments. Each one is called an arc second. So there are 60 arc seconds in every 1 arc minute. There are 60 arc minutes in every 1 full degree. So 1 arc second is a very, very tiny, tiny piece of the sky. And to put it into context, to give you a feel for what it is, if you were able to see how big 1 arc second appears to the human eye, it would be the equivalent of looking at the size of a dime that somebody's holding in their hand, holding up at a distance of 2 kilometers. Imagine somebody 2 kilometers away holding up a dime. The appearance of the size of that dime would be the appearance of something with the size of 1 arc second. Very, very small. You would never see that with the human eye. Now that's what an arc second is, and here's why I'm showing you this. So let's do some examples. For instance, let's compare the resolution capability of the human eye compared to something like the 200-inch Hale telescope at Palomar Observatory. We're going to choose a wavelength that's right in the middle of the visible spectrum. So we're going to choose a wavelength of about 5,000 angstroms, and what we're going to do is convert that into centimeters. So 5,000 angstroms equals this many centimeters here, and let's do some calculations here. We're going to plug in our formula. So this is the D. The typical diameter of the opening of your eye is about 0.3 centimeters. This is the constant of proportionality that makes everything work. It's just a number that never changes. And we're going to use the wavelength of 5,000 angstroms. So notice the angular resolution of the human eye is 42 arc seconds. This little double dash is the symbol for arc seconds. Now remember, 1 arc second is the size of a dime seen at a distance of 2 kilometers. So your eye cannot see anything smaller than 42 arc seconds across, meaning you will not see a dime at 2 kilometers away, because again, that's 1 arc second. So the human eye can only resolve things that have a minimum size of 42 arc seconds. If we use the Hale 200-inch telescope and do the same calculation, the difference now is that the size of the mirror, the size of the opening of this telescope, has a diameter of 508 centimeters. What you can see is running the numbers, we get 0.025 arc seconds. Remember, smaller is better. So we can actually see much, much smaller objects with clarity and detail when we have a much, much larger telescope looking at these objects. If we do a ratio, in other words, compare what we can see with the Hale 200-inch telescope with your human eye, the ratio of these two numbers is 1,680. In other words, the ability to see fine details is almost 1,700 times better when you use a large telescope like the 200-inch at Palomar Observatory. So the ability to see fine details in the objects that we're studying, the objects that we see in the sky, is a very critical thing. The more detail we can see, the more information we gather. And remember, bigger is better when it comes to the size of the telescope. A bigger telescope gathers more light, making faint things appear brighter. A bigger telescope allows you to see smaller details in very, very distant small objects. So now you can see why astronomers are always concerned with building bigger and bigger telescopes. And as the years go by, you will see a continual progression as astronomers outdo themselves. Next year's telescopes will be bigger than this year's telescopes. And 10 years from now, they'll be bigger than they are next year. And I imagine in 20 or 30 years, the telescopes on Earth are going to be very, very large, and the amount of information we're going to get is going to be enormous. Now, in the next video, what we're going to talk about is why do astronomers put themselves in very, very high mountaintop places to be able to see the stars and the information that's there. And we'll talk about why those locations are specific and why they're important, and we'll get to that in that video. I hope you'll join me then.